Somewhere on the coast of the Red Sea, a concrete spine is climbing toward a number no building in human history has ever reached. Not 800 meters, not 900, a full kilometer, 3,000 feet of steel, concrete and glass, stacked straight up into open sky. Here's what should bother you about that. The engineering needed to build something this tall has existed for decades. The concrete mixes, the wind-shaping techniques, the deep foundations that keep a tower from sinking into soft ground, all of that was solved knowledge by the 1990s. So why did it take until now for anyone to actually attempt a kilometer? Because for almost 70 years, one component hidden inside every tall building on Earth quietly decided how high we were allowed to go. It wasn't the wind battering the upper floors, it wasn't the money, and it wasn't even the ground underneath. It was a rope, an ordinary steel cable, hanging in an empty elevator shaft, doing a job it was never built to survive. By the end of this video, you'll know exactly what that rope does, why it nearly killed the dream of a kilometer-tall building for good, and how one company spent 7 years quietly replacing it with something that weighs a fraction as much. A change that just unlocked the next 500 meters of the sky, and possibly the 500 after that. To understand why that rope mattered so much, it helps to look at how fast the height record has actually moved. The Eiffel Tower held the title of tallest structure on Earth at 330 meters back in 1889. Barely 40 years later, the Empire State Building cleared 380. A few decades after that, towers in Kuala Lumpur and Chicago pushed past 450, and the current record holder, the Burj Khalifa, clears 800, nearly a full kilometer, reached in under a century and a half. If you draw a straight line through that progress, a kilometer-tall building should have existed years ago. It didn't, and it's not because nobody tried. It's because somewhere past 800 meters, one quiet piece of hardware kept saying, no. First though, let's look at what's actually rising in Jeddah right now, because the story of this building is stranger than the tower itself. The tower was designed by Adrian Smith, the same architect behind the current record holder, the Burj Khalifa in Dubai. It was originally called Kingdom Tower, before the name quietly changed to match its city. And its construction history is not a straight line. In 2018, work simply stopped, roughly a third of the way to its final height. For almost 7 years, the cranes sat frozen and no concrete was poured, a casualty of financing trouble and a change of contractor that left the entire project in limbo. What saved it wasn't a new investor, it was a rebrand. Saudi Arabia folded the tower into Vision 2030, its flagship plan to build an economy that doesn't depend on oil, and the half-finished tower became the plan's tallest advertisement. Construction restarted in January 2025 under a new manager, the American firm Turner, with more than 5,000 workers now on site, adding roughly 1 floor every week. By early 2026, the tower had passed its 100th floor. At the current pace, it should clear the 500-meter mark within about 6 months, on its way to roughly 160 floors and a planned finish in August 2028. When it's done, it will stand more than 3 times taller than the Eiffel Tower and nearly twice the height of the tallest building in the United States. Notice what's missing from that story: a shortage of land. The tower isn't going up because Jeddah is running out of space. There's empty ground for miles around the site. It's going up because a record can only be claimed once, and Saudi Arabia wants to be the country holding it. The tower anchors a new business district covering more than 5 million square meters, meant to pull companies, tourists, and capital into a patch of desert that had none of those things before. Inside, there will be a 4 Seasons hotel, high-end apartments, premium office space, and, this part matters more than it sounds, the highest observation deck on the planet, a single attraction the Burj Khalifa's own viewing decks prove can bring in millions of paying visitors a year on its own. turning a few hundred square meters of floor at the top of the building into some of the most profitable real estate anywhere in the country. The tower itself will cost over $1 billion. The district around it will cost many times more. None of that spending is really about square footage. It's about owning a number that nobody else can ever own first, and a record like that only has one winner, ever. Once this tower opens, tallest building on Earth belongs to Jeddah permanently, in a way that no amount of money spent afterward can undo. But wanting to build something this tall doesn't make it possible. Getting a building past 800 meters means winning a series of fights against physics that most structures never have to have. The first fight is with wind, and it doesn't behave the way you'd expect. Down at street level, a strong gust barely moves your jacket. 400 meters up, air behaves like a completely different substance. It doesn't just push on a tower, it curls around the back of it in rotating vortices, the same way water curls behind an oar pulled through a lake. Those vortices peel off one side, then the other, in a rhythm that can rock a tall building back and forth. At the top of the Burj Khalifa, that sway is large enough to move the structure almost 15 meters off-center, roughly the length of a dining table, at the very tip of the building. Engineers can't stop that sway with sheer strength, so instead, they've learned to outthink it. Some towers, like Taipei 101, hang an enormous steel pendulum, literally hundreds of tons of steel suspended near the top, that swings opposite to the building's motion and cancels it out. Jeddah's tower and the Burj Khalifa use a quieter trick: shape. Both buildings are built with a tri-lobed footprint, like a three-petaled desert flower, specifically so wind sheds off in mismatched, chaotic bursts instead of one clean rhythm. The shape was tested for months in wind tunnels against simulated gusts of 200 kilometers an hour, and today, sensors mounted near the top of the Burj Khalifa track its sway in real time, down to the millimeter. According to Thornton Tomasetti, the firm running Jeddah's structural engineering, the real building is swaying exactly the way those wind tunnel models predicted, months before it even reached its current height, which means, for once, the wind problem was solved on paper before the first floor went up. The second fight happens underground, before a single visible floor exists. Soft, waterlogged coastal soil can't hold a kilometer of concrete on its own, so engineers pour a raft of concrete 5 meters thick, about the height of a 2-story house, and drive it into the ground on 270 piles, each roughly 2 meters across, sunk more than 100 meters down until they hit solid rock. That's nearly twice as deep as the foundation under the Burj Khalifa, whose raft runs about half as thick, because Jeddah's ground is that much weaker. Proof that the same building, moved to a different stretch of coastline, can face a completely different fight underground before it ever faces one in the wind. Getting concrete up to where it's needed is its own separate war. On the Burj Khalifa, a German company set a world record, pumping concrete 606 meters straight up through a pipe, like squeezing toothpaste through a tube 2 Eiffel Towers long. In the desert heat, ordinary concrete would set before it even reached the top, so crews poured at night, sometimes packing the mix with ice just to keep it workable long enough to make the climb. Even the cranes carry a strange problem inside them. On the Burj Khalifa, 3 of them worked at once, each capable of lifting 25 tons and holding steady in winds up to 120 kilometers an hour, together hauling more than 60,000 tons of steel and material skyward over the life of the project. They climbed the building by growing their own mast section by section as the tower rises, which is straightforward on the way up. But once the tower is finished, and there's no taller crane left to lift the last one down, engineers solve it almost like a puzzle. The crane lowers its own highest sections first, shrinking itself piece by piece, until a smaller crane, positioned lower down, can take over and disassemble what's left. None of that even accounts for the workers themselves, On the Burj Khalifa's build, a round trip to the upper floors in a temporary hoist could eat up 35 minutes, and at the project's peak, 12,000 people showed up to the site every single day, adding up to roughly 22 million hours of human labor before the building was done. And once the tower is actually finished, it inherits a whole new set of problems that only exist because it's this tall. Warm air, trapped inside a kilometer-high shaft, rises just like smoke in a chimney, creating enough pressure at the entrances and the roof to jam doors and whistle through gaps, which is why revolving doors and airlocks aren't a style choice. They're load-bearing parts of the climate system. The glass skin on the Burj Khalifa, nearly 26,000 hand-cut panels covering more than 120,000 square meters over 20 football fields of glass, needs constant, endless cleaning. A crew of 36 people takes 2 to 3 months to wash the entire building, and by the time they finish, the bottom is already dirty again, 4 full cycles a year, forever. And because nobody can walk down 160 flights of stairs during a fire, the building needs pressurized refuge floors roughly every 25 stories, about 6 of them stacked up the height of the tower, so people have somewhere safe to wait instead of somewhere to run, alongside a dedicated firefighting elevator built to keep working even while everything else in the building is being evacuated. All of that, the wind, the foundation, the concrete, the cranes, the fire systems, engineers had already solved by the time the Burj Khalifa opened in 2010. None of it is what kept the kilometer mark out of reach for another 15 years. The real ceiling was hiding in the one place nobody was watching, the empty shaft where the elevator hangs. Steel is strong. That was never in question. The problem is that steel also has weight, and once a cable gets long enough, that weight starts working against itself. A steel elevator cable, stretching past roughly 500 meters, begins to approach the point where it can no longer support its own mass, let alone a loaded car. It starts to tear itself apart from the inside, under nothing but its own hanging weight. To lift a 2-ton elevator cabin in a 500-meter building, you need a steel cable weighing close to 30 tons, about the weight of 5 adult elephants, meaning the rope itself outweighs the thing it's carrying 15 times over. Push much past that length, and the math simply stops working. That single limit is the real reason no super-tall building runs one elevator straight from the lobby to the roof. Every one of them forces you to get out partway up, at what's called a sky lobby, essentially a vertical bus stop, and change cars, not because it's more efficient, but because the cable physically cannot go any further. Even the Burj Khalifa, the tallest building on Earth, tops out at a 504-meter single elevator run. That's not a design choice. That's steel hitting its ceiling. This is not a new problem. Back in 1956, the architect Frank Lloyd Wright unveiled a design for a building called the Illinois, a tower over 1.5 miles tall, more than double the height of anything being planned in Jeddah today. It was never built, and while people usually blame the idea's ambition, the real obstacle was smaller and far less dramatic. Nobody had a rope that could climb that high without snapping under its own weight. For nearly 70 years, that was the whole story. Every clever trick with concrete and shape and foundations bought a building another 100 meters, but the rope in the shaft was always the last word. The company that finally broke that ceiling wasn't a construction firm at all. It was a Finnish elevator manufacturer named Kohn, and their fix wasn't a stronger metal. It was a completely different material. Instead of a round steel cable, they built a flat belt with a core made of woven carbon fiber, a project they spent about 7 years developing before it ever left the lab. At equal strength, that belt weighs less than a fifth of the steel it replaces. The same 30-ton cable needed for a 500-meter shaft becomes a 13-ton belt, and unlike steel, it can keep going for another 500 meters after that, in a single continuous shaft, with no sky lobby and no forced transfer. The belt barely stretches over time, doesn't need lubrication, lasts roughly twice as long as a steel cable, and even saves close to 15% of an elevator's energy use at the 500-meter mark alone, because it's simply not dragging as much dead weight up and down all day. It was tested for years in a purpose-built shaft more than 300 meters deep in Finland, then proven for the first time in 2013 in a major Singapore skyscraper before it ever went into a real building at this scale, and it's now the elevator system chosen for the tower rising in Jeddah. The building will push that technology further than anywhere else on Earth. Its elevators will run in double-decker cabins, 2 rooms stacked together, boarding from 2 floors at once, doubling how many people move per trip, without needing extra shaft space. One elevator run inside the tower will stretch roughly 660 meters without a single transfer, the longest uninterrupted elevator ride ever built, beating even the Burj Khalifa's own record run. Cabins will travel at 10 meters per second, covering more than 500 meters in under a minute, fast enough that passengers' ears will pop like they're taking off in a plane, which is exactly why the cabins are being built with the same kind of gradual pressure equalization used in aircraft. None of this works in isolation either. A kilometer-tall building needs dozens of elevators and escalators just to move people between the sky lobbies, and entire mechanical floors, sealed off between the residential levels, packed with pumps and air handling equipment most residents will never see. Water can't simply be pushed a kilometer straight up from ground level. The pressure at the bottom of that pipe would burst it long before the water reached the top. Instead, it gets relayed upward in stages, floor by floor, handed off from one pump to the next, the same basic principle that keeps the elevators from trying to do the whole climb in a single impossible leap. So the kilometer mark, when it finally falls, won't fall because of a stronger kind of steel or a cleverer shape cut into the wind. It will fall because someone replaced 30 tons of rope with 13 tons of woven carbon, coiled thin enough to carry in one hand. And it doesn't stop at 1 kilometer. Plans already exist for a tower nearly twice this height, rising in Riyadh, and once again, the real obstacle won't be the wind or the ground. It will be whatever the elevator is hanging from. At least one company is already testing elevators that use no cable at all, cabins riding on magnetic tracks inside the shaft. The same basic principle as a maglev train, free to move sideways as easily as up, with several cars sharing a single loop instead of each one waiting on its own rope. If that technology works at the scale a 2-kilometer tower would demand, the last number that's ever limited how tall we build, the weight of the thing holding the elevator up, disappears completely. Every wall in this story, the wind, the soil, the concrete, the crowds of workers riding hoists for half an hour just to get to work, got solved by people who were looking directly at it. The one wall that held for 70 years was the one nobody thought to look at twice, because it wasn't dramatic. It didn't howl like wind or crack like a foundation. It just hung there quietly, doing math against itself, 1 meter at a time. So here's the real question worth sitting with. For 70 years, the ceiling on human height wasn't the sky, the ground, or the wind. It was a rope nobody was watching. If something that quiet was able to unlock the next 500 meters, what do you think unlocks the next 5,000? A stronger material, a system with no cable at all, or something we haven't even thought to look for yet? Drop your answer below.